Elevators are a common mode of vertical transportation in modern buildings. While the passengers of elevators are familiar with the elevator car and few buttons, the hidden internal mechanisms involved are somehow complex and interesting. An elevator in its simplest form can be represented by the illustration shown here. An electric motor turns a pulley and a flexible rope winds or unwinds along which the elevator car rises or lowers. Similar components are assembled in an actual elevator with some modifications. It contains a braking system and a worm wheel mechanism, which will be explained momentarily. First, let's discuss about an integral component known as counterweight. The counterweight travels along vertical guide rails opposite to the direction of the elevator car. This component may appear to do nothing more than just rising and descending, but it in fact plays a very crucial role in the stability and energy efficiency of an elevator. Let's observe our previous demonstration. Here, raising the car will require very high torque. Once the car is raised, extremely powerful brakes will be required to maintain the car's position or to lower the car in a controlled manner. This is why the counterweight is introduced. The basic idea of counterweight is that if there are two equal weights attached to either end of a cable, then the system is perfectly balanced. The only job of the motor is to tip the balance one way or the other. However, in an actual elevator, the load on the car changes with the number of passengers, but the weight of the counterweight remains constant, which creates certain imbalance in the system. To minimize this imbalance, weight of counterbalance is determined by using a formula which is explained at the end of this video. Let's first discuss about the safety devices provided in elevators. A wheel is attached to the shaft of the motor with two brake arms on either side of the wheel. An electromagnetic system and a spring is used to disengage and engage the brakes. While this setup seems like a normal electromagnetic braking system, it works in an opposite way in elevators. In a typical electromagnetic braking system, the electromagnet engages the brakes and the spring disengages it by retracting the brake arms to their initial position. But in elevators, the spring engages brake when the elevator is at stop, and the electromagnet disengages the brakes as long as the car is traveling. The advantage of this system is that if there is a sudden power failure or malfunction in the electric system, the brakes will engage mechanically with the help of spring, and the elevator car comes to a safe stop without relying on electrical systems. Next to this brake sits a worm wheel mechanism. It has a very high gear reduction ratio. It can convert low torque, high speed motor input to a very high torque, low speed output. This is ideal for an elevator because the elevator car doesn't need to travel fast, but it definitely requires high torque to operate. The other advantage is that this mechanism is self-locking, which means the back drive of worm gear by the wheel is not possible, which prevents unwanted traveling of car. Elevators are provided with multiple steel cables to hold the carriage and the counterweight. Technically, only one of these cables can hold more load than the carriage and counterweight combined. Multiple cables are provided so that the elevator can safely operate, even if a few of them snap accidentally. But what if the worst happens and all these steel cables suddenly snap at once? If this happens, the counterweight will free fall and hit the cushioning buffers at the bottom. But the car will still not plunge to the basement. This is because a set of backup brakes are provided at the bottom of the car. These brakes are controlled by a component called overspeed governor. It is a combination of a sheave and a centrifugal braking system. A cable runs along the sheave, which is connected to a lever in the braking system. In normal conditions, the brakes follow the car and the brake lever pulls on the cable, as shown here. During this time, the centrifugal brake arms are free and rotate with the governor sheave. But if the main cables snap, the car starts falling rapidly and causes the governor sheave to spin quickly. When the sheave exceeds rated speed, the arms fly out and lock with teeth in the stationary casing. This suddenly stops the sheave and cable. As the cable stops, the brake lever is pulled upwards. This pulls the two wedged brakes and clamps them upon the guide rails. This wedged system of brakes is very powerful and prevents the car from falling. Now let's discuss how the weight of counterweight is determined. For a balanced system, the weight of counterweight should be equal to the weight of elevator car. When some load is added to the car, same weight should be added to the counterweight to balance the system. But we can't simply change the weight of counterweight for each loading conditions. This means the system will remain unbalanced most of the time. So the job of counterweight is just to reduce this imbalance to minimum. So weight of counterweight is determined by adding the weight of the car and half of the total capacity of elevator. Let's understand this by using a simple example. Let's suppose the full capacity of elevator is 4 people. According to the formula, counterweight is equal to car plus 2 people. When elevator is fully loaded, there is an imbalance of 2 people. When elevator is not loaded, there is again an imbalance of 2 people. This means the imbalance never exceeds 2 people, and the system remains at maximum balance under variable loads. The other significance of this formula is that, in real life, elevators are generally loaded to a fraction of its capacity, which is close to half of its capacity. So the system remains at maximum balanced condition all the time.